Good morning everyone. So, we are discussing about the dialysis, and in the last class whatever we have seen how the design equations of a continuous dialyzer are derived and how we are going to utilize and what are the various internal parameters that will be required to design this dialysis to design a dialyzer. And we looked into that from the flow geometry and the flow regime, one can get the mass transfer coefficient in the feed side and in the dialyzer side, and there are the resistance that is offered by the membrane phase. There is only one parameter that requires a separate set of experiment to be conducted, that is the diffusivity of the solute through the membrane phase. For that we have one can undertake an experiment which is in a batch mode, okay, and which is pretty easy to conduct. And using the batch mode experiment and the data that is obtained from the concentration profile that is obtained from the dialyzer side, one can rearrange the equation and can plot the concentration profile suitably, and one can get the value of diffusivity through the membrane phase. Now, in today's class, first we will look into one aspect of the batch dialyzer. In batch dialyzer, what happens that when the solute concentration from the feed gets transported to the dialyzer side, then what happens, the concentration in the dialyzer side goes on increasing. So, as time of operation progresses, the concentration difference or concentration gradient decreases. So, in order to prevent that, one can use some solutes in the dialyzer side which will react with the solute that will be getting transported to the dialyzer side. So, therefore, the concentration of the solute in the dialyzer side will always be maintained at 0 level. So, that will maintain the maximum concentration difference. So, the transport of the solute through the dialysis will be enhanced. So, therefore, in today we will first talk about the enhancement of separation in dialysis by secondary chemical reaction. We will allow a secondary chemical reaction to occur in the dialysis site with the solute that is coming from the feed chamber, so that the concentration remains 0. So, in the dialyzer chamber, we have to select a dialyzer such that the diffused components react and product ions are not cannot diffuse back. So, therefore, a maximum concentration difference, maximum concentration gradient is maintained. I will just take up one example. Aniline plus H2SO4 gives you anilinium ion. It forms a complex. So, if you would like to remove aniline from the feed site and in the dialyzer, so aniline is there in the feed site and in the dialyzer site you will be having sulfuric acid solution. So, aniline crosses over the membrane and comes to the dialyzer site. It reacts with the sulfuric acid present in the dialyzer site, forming the anilinium ion. This anilinium ion is bigger in size, it cannot diffuse back to the feed chamber. So, therefore, in the dialyzer site, the concentration of aniline will be always remain at the minimum level. Okay. So, that provides a maximum concentration difference across the membrane. Call this as component 1, this is component 2, this is component 3, and component 2, that means H2SO4 is always in excess such that the reaction is always complete. Okay. Is always in excess, so that reaction is complete. So, the essence of this idea is that aniline diffuses through the dialysis membrane, comes to the dialyzer site, immediately it reacts to sulfuric acid, forming the anilinium ion. So, therefore, in the dialysate side we are maintaining a 0 concentration of aniline. So, therefore, the concentration gradient across the membrane is maintained as maximum. Now, what we will do? We will write a mass balance equation in feed chamber. Mass balance means in terms of solute balance basically. In feed chamber, Vf d C1f dt is equal to minus Am Dim over L C1f minus C1d. 1 represents the aniline concentration. So, therefore, this is a aniline mass balance in the feed chamber. The accumulation that is there, it is basically negative accumulation, because in the feed chamber the amount of aniline is decreasing. C1f and C1d is the concentration of the aniline in the feed and the dialysate chamber respectively at any point of time. This equation can be rearranged as d C1f dt is equal to Am Dim over L times Vf C1d minus C1f. This minus sign is absorbed within the bracket, and aniline balance or solute balance in the dialysis chamber becomes d C1d dt is equal to Am Dim times L times Vd C1f minus C1d minus d C3d over dt. So, in the dialysate chamber what we have? We have the gain in the aniline concentration that is coming from the feed side, as well as there is a sink term present in the dialysate side, which indicates there will be a Vd, I guess, which indicates that there will be decrease in the this is basically consumption of aniline because of presence of formation of the anilinium ion. It reacts with the sulfuric acid. So, there is a sink term present there. Now, we consider we define Am by Dim over L as a constant k. So, these two equations, I think there should not be 1 by Vd there. So, these two equations can be written in a much more compact fashion and in terms of k. Okay. So, if you do that, this two equation becomes d C1f dt is equal to k divided by Vf C1d minus C1f d C3d dt plus d C1d dt is equal to k by Vd C1f minus C1d, where the subscript f stands for the feed side and subscript d stands for the dialysate side. Now, we have the initial conditions. So, this is an ordinary differential equation and the initial conditions are specified. The initial conditions are at time t is equal to 0, you have C1f is equal to C1f naught. That means, initial concentration was C1f naught. At time t is equal to 0, you have C1d is equal to 0. That means, there is at the start of the process there is no solute crossing over to the dialysate side, and C3d is equal to 0, because there was no solute present in the dialysis site, there is no chance of having a reaction. So, the component 3, that is the anilinium ion, the concentration of that will be equal to 0 at time t is equal to 0. Now, at any time t, the concentration of anilinium ion in the dialysis site is in equilibrium, because the reaction is in equilibrium, and you have the equilibrium in terms of equilibrium constant, you can express the concentration as C3d divided by C1d times C2d. So, this is the concentration of anilinium ion, this is the concentration of aniline in the dialysate site, and 2 is the concentration of sulfuric acid in the dialysate site. This equilibrium relation gives you the concentration. So, that will be a constant for a particular temperature. So, this gives a relationship between the anilinium ion and concentration of the aniline in the dialysate chamber via this equation, where C2D is the concentration of sulfuric acid. Since it is in excess, this concentration will be treated as constant. Okay. So, C2D is constant as it is in excess. Okay. So, therefore, we can solve these two equation and expressing C3D in terms of C1D and equilibrium constant in this equation. So, let us see how we will do that. So, what we will take, again we take the Laplace transform. This is a coupled ODEs. So, take Laplace transform of this equation and the transformed, and we can work with the transformed equation. If you take the Laplace transform, the following two equations are resulted: k over Vf times C1D minus C1f bar. This bar stands for the transformed quantities S C1f bar minus C1f naught. K by Vd is C1f bar minus C1d bar is equal to S C1d bar minus C1f naught plus S C3d bar minus C3d 0. So, these will the Laplace transform of the two equations will result these equations, and one can simplify these two equations and can get an expression of C1d bar. So, because basically we are going to monitor the concentration of the aniline in the dialysate site, we just take up a sample and analyze it. Okay. So, if you do that, you will be getting k by Vf C1d bar is equal to k over Vf plus S into 1 plus Vd over k 1 plus C2d times S C1d bar minus C1f naught. And remember that the thing within the third bracket becomes completely constant because C2d is in excess. So, therefore, it can be treated as constant. Okay. You can rewrite this equation on simplification. On simplifying, finally, you can get an expression something like this: C1d bar is equal to C1f naught is equal to As divided by As plus Bs square, where the term A is defined as Vd by Vf 1 plus C2d. Since Vd and Vf are the volumes of the feed and the dialysate chamber, and C2d is constant, the value of A is also constant. V is equal to Vd over k 1 plus C2d. Okay. Now, this equation can be the terms in the denominator can be represented in the form of 1 plus 1 over S minus 1 over 1 plus k plus S, something like that. So, what I mean, this fraction, the denominator can be represented as a summation or subtraction of real fractions. Okay. Then one can take the inverse Laplace transform and can get the expression of how the concentration of sulfuric acid is varying as a function of time in the dialysate chamber. Okay. So, one can take the inverse Laplace transform and one can get the C1d as a function of time. I am not doing that. You please carry out this exercise by yourself and find the concentration profile in the of the solute in the dialysate site. Okay. So, let us now summarize whatever we have done till now. We have got the definition, we have defined the dialysis process, and we have analyzed the various mass transfer resistance that will be coming across the dialysis process. various mass transfer resistances. Then we looked into the design aspects of counter current dialyzer. And in the counter current dialyzer, we have found out there are 3 resistances that have to be determined. One is the mass transfer coefficient in the feed side, mass transfer coefficient in the dialyzer side, and membrane resistance. Out of these 3, 2 can be easily obtained by looking into the flow regime and expression of Sherwood number relations. Now, on the other hand, the parameter, the diffusivity through the membrane phase, can be estimated by a separate set of experiment in a batch dialyzer, and how important this batch dialyzer is, because the importance is that it gives you the concentration, it gives you an important parameter, that is the diffusivity of the solute through the membrane phase, and which will be utilized in the design equation of the continuous counter current dialyzer. So, using this information, step number 1 to 4, you will be able to really should be able to design a dialyzer. Okay. And today we have just learned how the performance of batch dialyzer is improved. Okay. So, what we have to do in that case? In that case, in the dialyzer chamber, you give some material, some chemical, which will be reacting with the solute that is getting transported in the dialyzer side, so that the concentration of the solute will always be maintained at 0 and a maximum driving force will be maintained all the time. Now, the design of continuous dialyzer in the counter current mode, that whatever we have done till now, that is one dimensional model, but that is good enough to get a first hand information on the design of the dialyzer. Now, but for the sake of completeness and for the scientific interest, one has to go into the 2 dimensional model or more complicated model of the steady state dialysis process. Why it will be required? It is required because the channel, the dialyzer channel and the feed channel, that whatever we have, actually in one dimensional model we are considering the velocity profile is flat, that means it is something like a plug flow. So, we are talking about the cross sectional average velocity, and we are evaluating the mass transfer coefficient etcetera from the cross sectional average velocity. Also, we are assuming that the concentration profile that is existing in the system, in the channel, is always it is one dimensional, it is constant. In fact, the bulk concentration is constant, there is no profile existing there, which is not the actual case. If you talk about more scientific terms, both velocity field and concentration field, even under fully developed region, will be function of y, or in the transverse direction in the channel. So, in one dimensional case, we are neglecting the variation of the concentration and the velocity profile. In the 2 dimensional case, we will be including the actual velocity profile and concentration profile in the channel. In fact, we are utilizing the fully developed velocity profile, and we will be deriving the concentration profile, and from that expression we will be doing a length cross sectional averaging. It is called cross sectional averaging, that is called cup mixing concentration or cup mixing temperature. If you remember the concept of the average temperature or concentration in case of heat transfer or mass transfer. In an actual case, if you would like to take out a sample, or if you would like to monitor the temperature at a particular location, okay, or if you would like to measure a concentration, you cannot get the instantaneous point value of the temperature or concentration. Okay. So, what you have to do, you will be able to measure, that will be the cross sectional average value. So, once you get a profile, you have to average it out over the cross section in the y direction, and that particular value after the averaging is known as the cup mixing temperature in case of heat transfer, or cup mixing concentration in case of mass transfer. So, these are the measurable quantities. Okay. So, we will be getting the expression of that, and from that we will, from the first principle we will look into the dialysis performance and its efficiency, and from that we can design a dialyzer more accurately. Okay. So, let us look into the detailed two-dimensional analysis of dialysis. Okay. So, the x starts from here and it is up to L. This is the dialysate site and this is the feed site. Okay. The blood enters here with a profile something like this. It's a fully developed parabolic velocity profile, blood going into the system under the laminar flow condition. Okay. This is the half channel height. Let us say this is h, and we set our coordinate system in this case in the middle of the channel. That will simplify our life as far as the mathematics is concerned. So, that is in the center, and the concentration profile is also a parabolic one. If you solve, you will be getting a more or less parabolic concentration profile. So, in the earlier case we have considered the velocity profile is flat and the concentration profile is also flat. So, this is a typical dialysis the concentration and velocity profile in a rectangular geometry in a dialysis system. For a Newtonian fluid, the velocity profile becomes u times y is equal to 3 by 2 u naught 1 minus y square by h square. That is the profile of the velocity in rectangular channel. So, let us say h small h is the half height of the channel, okay, and y is at the middle plane. So, this comes from the Navier-Stokes equation, solution of Navier-Stokes equation or equation of continuity. Okay. And we also assume that the channel width is very large compared to the channel height, okay, and mass transport is therefore two dimensional. Now, Q is 2 u naught W times H. What is this Q? Q is the flow rate of the blood, and u naught is the cross sectional average velocity, and it should be multiplied by the area of cross section W times 2 h. Okay, W times 2 h, we wrote small h as the half height, W times 2 h will be the full height. So, that gives 2 W h will give you the full cross sectional area, which is normal to the direction of the flow of the material. So, you can put a rotameter in one of the lines and can measure the velocity, measure the flow rate, and divide the flow rate by the cross sectional area, because the channel geometry etc. are known to you. So, you can estimate the value of u naught. Okay. Now, at the steady state, we can write down the solution solute mass balance for y lying between minus h to plus h. We write down the solute mass balance. That will be simply u del c del x is equal to d del square c del y square. Okay. If you remember, when we were talking about the pressure driven membrane based separation processes, we wrote down the concentration balance equation within the mass transfer boundary layer. There was an extra term here, that was plus v del c del y. Why that term was appearing? That term was appearing because there is a transmembrane pressure drop. Because of the transmembrane pressure drop, there was convective flow of the solute towards the membrane surface. but in the case of dialysis, since there is no transmembrane pressure drop, it is the driving force is only concentration gradient, the velocity component in the y direction does not exist. Okay. So, it will be u del c del x is equal to d del square c del a square, and if the term on the left hand side, the second term which appeared earlier, that will be turning out to be 0. So, we require to have one boundary condition at x is equal to 0 and two boundary conditions at on y. Okay. So, at x is equal to 0, we had c is equal to c naught, that is the feed concentration that is going into the system, and at y is equal to 0, you had del c del y will be equal to 0. That means, the concentration profile is undergoing a maxima at the central line. This is also known as the symmetric boundary condition. Okay. So, you have the concentration profile something like this. So, the maxima will be going at the middle of the channel. So, at the middle of the channel, since it is maxima, del c del y will be equal to 0, and at y is equal to h, let us say the molar flux of the solute is given as P times C. Okay. What is P? P is nothing but the membrane solute permeability through the membrane. Okay. So, and that has to be this solute permeability through the membrane, that means P times C, and we are assuming that concentration in the dialyzer site will be equal to 0, because the dialyzer fluid is maintained at sufficiently high speed. So, that the whatever the solute that is travelling to the dialyzer site, immediately it will be washed away. So, therefore, it should the molar flux of the solute through the membrane should be P times C at the membrane feed interface minus membrane dialyzer interface, but we are assuming that concentration will be equal to 0 in the dialyzer side, because the dialyzer fluid is maintained at sufficiently high velocity. So, that it becomes immediate, it will become 0 and it will be immediately washed away. Okay. That simplifies the whole analysis, otherwise one can put that and whole thing have to be solved numerically. Okay. So, let us look into okay. So, and that at the steady state that has to be P c, that is the it has to be matched by the solute diffusive solute flux towards the membrane. What is diffusive solute flux? That will be minus d dc del c del y, minus d del c del y, that is the Fick's law. So, that means amount of solute per unit time, per unit cross sectional area, that will be arriving at the membrane surface, it will be immediately getting transported to the other side via the solute permeability, because of the solute permeability present there. So, solute permeability P is a known quantity for you. So, now let us write down the so therefore, the condition, the boundary condition at y is equal to h becomes d del c del y plus P c will be equal to 0. And if you remember that this becomes almost the same boundary condition of the pressure driven membrane separation processes like reverse osmosis, ultrafiltration, etc. Only thing now is missing is there we had C minus Cp, but here we will not be having C minus Cd, because we are assuming Cd will be instantaneously equal to 0. So, let us write down the assumptions that we have made into this analysis. One is solute flux is positive if it is from blood to the dialysis site, and blood site is nothing but the feed site. Okay. The second assumption is the parameter P includes the effects of diffusivity of the solutes through the membrane. That means, the term dim by L, we are coupled, we are just coupling that term dim by L into the parameter P, which will be constant for a membrane solute system. That means, P is invariant, P is constant for membrane solute system. Third is the C, the concentration of solute in the dialysate site is close to 0. That means, it is extremely dilute. Okay. So, these are the various, and of course, the process is steady, it is a steady state process. So, now we are in a position under this set of assumptions where we can construct the governing equation and the boundary conditions. Once we do that, now let us write down some in terms of non-dimensional parameters and make the equation non-dimensional, so that the mathematical complexity will be much simpler. So, we define the non-dimensional terms variables as C star is equal to C by C naught, okay. Y star is equal to Y over H, and X star is equal to X times D U 0 H square, and P star is equal to P H over D, that is known as the membrane Biot number. Okay. How you obtain this X star? If you remember, the governing equation was del C del X is equal to D del square C del Y square, and these two are quite obvious, the definition of C star, because you know the known concentration C naught at the entry point, and the height of the channel is known. So, therefore, the dimension in the y direction is known to you. So, therefore, you can put this non-dimensional variable there. So, this becomes del C star del X is equal to D divided by H square del square C star del Y star square. Okay, there is one U was there. So, you can define as U star is equal to U by U naught. So, therefore, it will be U naught U star. So, multiply both sides by H square by D. So, it becomes U 0 H square by D U star del C star del X is equal to del square C star del Y star square. So, on the right hand side is fully non-dimensional, the left hand side U star is non-dimensional, C star is non-dimensional, that means this has to be a non-dimensional quantity. Okay. So, we define X star as X multiplied by D divided by U 0 H square. Okay. That is how the non-dimensional term of X star will appear in that particular form. So, that is true for any non-dimensionalization of any governing equation, because if there are some non-dimensional variables will be quite obvious to you, because in the some of the variables are coming from the operating conditions, some of them are known from the geometry. So, you can define those variables, but if some of the non-dimensional variable is not apparent to you, you just substitute the known non-dimensional variables there and try to make the whole equation non-dimensional, and the form of the non-dimensional variable which is not apparent to you, that will be automatically emerging. Okay. So, you can do that as well. Now, so let us write down the non-dimensional form of our governing equation and its boundary conditions. Three by 2 1 minus y star square del c star del x star is equal to del square c star del y star square. Okay. This is the governing equation, and the boundary conditions are c star is equal to 1 at x star is equal to 0 for all y star, del c star del y star will be equal to 0 at y star is equal to 0 for all x star, and del c star del y star plus p star c star is equal to 0 at y star is equal to 1 for all x star. Okay. Now, this equation, so what is the form of this equation? Is it linear or nonlinear? This equation, this is a parabolic partial differential equation, and the equation is linear. Okay. So, if you remember the definition of linearity or nonlinearity of any partial differential equation, if you have some terms in your governing equation which is nothing but the multiplication of dependent variable and its derivative. For example, if you would have obtained c star into del c star del x star, or the higher order derivatives del square del c star del x star raised to the power 2, order may be more, then those equations becomes nonlinear. But since y star is the independent variable and it is multiplied, so this equation is a linear parabolic partial differential equations. Those who have done my mathematics course in the earlier semester, it is, I think that is pretty apparent, obvious to them. Now, the boundary condition, this is of course a linear, and it is a non-zero, it is a non-zero homogeneous condition there at the entry point at x star equal to 0, and you will be having a homogeneous boundary condition at y star equal to 0 and a homogeneous linear boundary condition at y star is equal to 1. So, both the boundary conditions are homogeneous and linear, and the governing equation becomes linear. So, you must be having a separation of variable type of solution to this particular set of equation. Okay. Now, that analytical solution is not obvious. So, what is done, one can have a series solution in order to get the so it's basically it has to be solved by c star is equal to x star multiplied by y star. So, what you can do, you can separate, you can express the concentration as a product of two variable x and y, and the x varying part is assumed to be solely a function of x star, and y varying part is assumed to be solely a function of y star. So, if you put that in the governing equation, so this is called a separation of variable technique, and the idea of separation of variable technique is that you must be having your governing equation a linear one, the boundary conditions in y direction where it will be order 2, then it must be having the homogeneous boundary conditions at that direction. Okay. So, if you really do that, so this becomes 3 by 2 1 minus y star square y times dx star is equal to x times d square, this is x, right, d square y d y star square. Now, you can separate the variables 3 by 2. So, okay, 1 over x dx by dx star is equal to 2 by 3 1 over y star square okay, 1 over y d square y dy star square. In fact, it will be better if you take the 3 by 2 term on the left hand side. So, it becomes 3 by 2 1 over x dx star is equal to 1 over 1 minus y star square 1 over y d square y dy star square. Now, the left hand side is completely a function of x, the right hand side is completely a function of y, and they are equal, that means they are equal to some constant. Now, this constant can be positive, can be negative, or can be 0. Now, those who have done the mathematics course in the last semester, it is known to them that if this constant is 0 or positive, you will be getting a trivial solution, and you are not looking for that. So, therefore, this constant has to be a negative constant, let us say minus lambda square, where lambda are called the eigenvalues to this particular problem. Okay. Now, I am not going into detail of this solution. So, therefore, you can just get an idea of the solution. So, the x varying part will be 1 over x 3 by 2 1 over x dx star is equal to minus lambda square, and dx by x is nothing but minus 2 by 3 lambda square dx star. Okay. So, one can integrate this equation and can get the x varying part as. So, it will be a log of x, integration of this will be log of x, and after integration this x can be expressed as the exponential term. So, after integration you will be getting log of x is nothing but minus 2 by 3 lambda square x star, and there will be some constant c 1, and x becomes some constant c 1 exponential minus 2 by 3 lambda square. Let us say this is lambda m, m stands for mth eigenvalue, lambda m is nothing but mth eigenvalue of the system. Now, once you do that, now you will be able to now you will be you can solve the y varying part. The y varying part will be 1 over 1 minus y star square 1 over y d square y dy star square is equal to minus lambda square. So, this becomes d square y dy star square is equal to minus lambda square 1 minus y star square times y. Okay. And what are the boundary conditions? The boundary conditions of on y varying part must satisfy the boundary conditions on y in the original problem. That means, at y star is equal to 0, dy divided by dy star will be equal to 0, and at y star is equal to 1, you have dy star plus p star p star times y is equal to 0. So, you have the ordinary differential equation in terms of y, and you have two homogeneous boundary conditions. Okay. So, again this can be solved almost if this term would not have been there, then you could have solved it quite easily, but because of the presence of this term, the solution is not that straightforward. But still one can get an analytical solution. That analytical solution can be obtained by using a series solution. So, if you must be familiar with the series solution of the ordinary differential equations that has been taught in the probably in the first or second year. Okay. So, one can get a series solution to y varying part, and I am not doing that exercise here because I do not want to get into that involved mathematics, because our purpose is something else. So, therefore, I am just writing the overall solution in concentration. So, the final expression of concentration as a function of x star and y star becomes summation of a m, where m is equal to 1 to infinity exponential minus 2 by 3 lambda m square x star summation of a n m y star raised to the power n, okay, where n goes from 0 to infinity. Okay. Actually, this is the series solution, this summation basically coming from the series solution of the y varying part that I just discussed earlier. Okay. Now, lambda m are the eigenvalues to the system, and let us look into the removal of toxic materials, how that will be obtained. Per unit time, that means rate of removal, let us say it is in kg per second, that means concentrations are expressed in kg per meter cube. If that is the, so how it will be defined? It will be defined as the amount of concentration, the amount of material of the solute that is coming at the entry point, that means that x is equal to 0 minus the amount of solute that is present at any particular location. Let us say if it is after the length L, then it will be after the channel. Okay. So, it will be 2 u naught h w multiplied by C naught minus C C m. Okay. I will define C C m. Let us try to understand what it is. 2 times h times w will be basically the cross sectional area multiplied by the u naught, that will be giving you the flow rate, okay, meter cube per second. Okay, and it should be multiplied by the amount of solute, that is kg per meter cube will be cancelled. So, this volumetric flow rate Q multiplied by the C naught will be the amount of solute that is entering into the system, right. And what is CCM? CCM is the cup mixing concentration. Okay. If you remember the solution is in terms of x star and y star, okay, but we cannot take any point value at any sample and determine the value of the concentration at any point in the cross sectional area of the channel. So, if you take out a sample and measure it, what it will give? It will give you a y averaged value of the concentration, that is known as the cup mixing concentration. So, cup mixing concentration will be a function of x, but it will not be function of y, because you are averaging out the y dimension. Okay. So, cup mixing concentration at any location x star means it is the cross sectional average concentration at that particular location x star. Okay. So, what is the definition of cup mixing concentration? The definition is integration 0 to h, okay, half height, it is u naught u c, which is a function of x and y dy multiplied by 0 to h u dy. Okay. It is basically the amount of the solute that is coming, and it should be multiplied by 2, and it should be multiplied by 2, and the w will be cancelled out, and all these things will be cancelled out, 2 will be cancelled out. So, it is basically twice of that, this integral, because it is symmetrical in y direction. So, this gives this definition of cup mixing concentration gives you, that means you have u is a function of y only. So, since it is fully developed in the y direction, so it will be in the denominator, you will be getting a value. Okay. On the other hand, in the numerator, you are going to put the profile of u there, but c will be a function of x and y. So, therefore, after integration in the y direction, all the y variation will be gone. So, therefore, CCM will, but the x variation will be intact, because you are not integrating over the x. So, CCM, the concentration, the cup mixing concentration will be a function of x star, but it will not be function of y star, because it is averaged over the y. So, what we are going to do, we are putting it as 0 to h 3 by 2 u naught 1 minus y square over h square c. We are going to put the concentration profile we just obtained earlier in the last slide, 0 to h 3 by 2 u naught 1 minus y square by h square times dy. That is the definition of cup mixing concentration. Okay. You can define a non-dimensional cup mixing concentration by simply dividing it by concentration at the entry point. So, this CCM star will be nothing but CCM divided by C naught. Okay. Now, if you now really put the concentration profile there and integrate and multiply with this and carry out these integrations, what you will be getting is that I am just leaving it as an exercise to you. I am just writing the final expression of CCM star. The value of CCM star will be nothing but, after carrying out the integration in the y direction, will be nothing but 3 multiplied by A m, where m is equal to 1 to infinity exponential minus 2 by 3 lambda m square x star, another summation A n m divided by n plus 1 into n plus 3, okay, where the n goes from 0 to infinity. This series is coming from the solution of the y dimension, that is coming from the series solution. And what are the values of lambda? Values of lambda m, that is the eigenvalues of these problems, are obtained as the roots of the polynomial. What is that polynomial? I am just writing that polynomial. In this form, 0 is equal to p star minus 2 by 3 plus 5 by 12 p star times lambda m square plus 1 over 20 plus 1 over 45 p star lambda m to the power 4 plus. How you obtain this equation? We can obtain this equation by writing the solution on the boundary condition at y star is equal to 1. Okay. From that, one can obtain the characteristic equation of eigenvalues, and the roots of this equation will be giving you the lambda m. Okay, we will just so we will stop here. We will go to the we will take some break and go to the next class and see what are the implication of this equation as far as the actual design is concerned when we are talking about a 2-dimensional flow field in the dialysis chamber. Okay. Thank you.